Okay, question on the board here involves a velocity versus time graph. Right? I would like for you to write it down somewhere. Okay, you don't necessarily need to draw the graph or just kind of freehand it. Okay, but I would like you to answer the questions related to that graph here. Okay, so from the graph you need to determine whether acceleration is positive, negative, or zero. Okay, you need to calculate the value of the acceleration where it's not zero. And then lastly, tell me when, in terms of at what time, does the bird actually change direction? All right, so I want you guys looking on that here for the next couple minutes while I get the attendance done. Okay, and then we'll see how we're doing. But just so you're aware, this question, I put one like this on the unit exam every single semester without fail. Just wait outside, please. Okay, so you're going to get one like this, so you're going to want to have this one written down as an example, okay, and then pay attention carefully when we go over it. First off, it's a velocity versus time graph, okay? The first two things it wants us to do is that we want to calculate what the accelerations are when they're not zero, and then identify all these places. So let's first off identify places on the graph where the acceleration is in fact zero. All right, what sections of this graph is the acceleration zero on?
B, D, and F.
B, D, and F. Okay, remember, this is a velocity versus time graph. Anywhere where the line is flat, the velocity is unchanged, which means it's not accelerating, because the definition of acceleration is a change in velocity over time. So if it's flat, the velocity is not changing. So B, D, and F are areas where acceleration is zero. All right, so we got that part done. Next thing it says is calculate the acceleration where it isn't zero. So during part A, the object is accelerating negatively, right? That is, it's going faster south, because the north is our positive direction here. All right, if I want to calculate acceleration, and it's not like a perfectly linear graph, then I want to use this formula. Okay, A equals VF minus VI over T. I can use that for part A because I know that VF is 4, negative 4 actually, okay, and VI is negative 2, so minus negative 2.0, okay, and then we divide that by how long that takes, 1 second. So negative 4 minus negative 2, right, is a change in velocity of right, negative 2 meters per second, negative 2 meters per second. Okay, and that takes 1 second, so our acceleration during that time is negative 2.0 meters per second squared. Okay, and instead of saying negative, since we were actually given a direction, we would say south. Okay, because the direction given to us was south and north. Everyone all right with that? So the next place where an acceleration is going on is part C. Okay? Now, in part C, we go from negative 4 to negative 6. Okay? So if we want to use this formula again, right, we're going to have VF minus VI over T, same as before, okay? And that's going to mean negative 6 minus negative 4, okay, divided by, and again, that's going to take from 3 to 4 seconds, so 1 second. Is it the same as what we just did? Okay, should I be able to recognize that from the lines? They have the same slope, don't they? Right? They look pretty much the same. All right, so that's also going to be 2.0 meters per second squared south. All right, next place where this thing accelerates is during section E. Right? And there's a lot of acceleration. There's a very big change in velocity during section E. We go from negative 6, which is our initial velocity, to positive 6. Right, so we want to use this formula again. A equals VF minus VI over T, and we're going to have 6 minus negative 6, okay, divided by the time. That goes from 7 seconds to 10 seconds, so over 3 seconds. All right, so we're going to have 6 minus negative 6 is 12, positive 12, okay, divided by 3. So our acceleration there is going to be 4 meters per second squared. Which way? North. Okay, because this time it ended up positive. All right, everybody okay with that? You understand how that works? All right. Most people get that part right when I put a question like this on the test. Part C is the part they get wrong. requires no calculation. It's just recognition from the graph. Okay? When does the bird change direction? So it's initially flying south, but by the end of this graph, it's flying north. At what time does it actually start flying north?
At point D and E, or something.
Here?
Yeah.
That's the most common answer I get. Unfortunately, it's not right. But we recognize that at that point, there is a change. Okay? The change is that now we're accelerating which way? North. So the acceleration becomes northward at this point, but its velocity is still negative. It's flying south as long as the velocity is negative. So it's actually right here where the bird changes direction. Okay? It's slowing down, slowing down, slowing down, slowing down, and now it's going north. Okay? So it would be like if I ran into a bungee cord. Okay? So if I had a bungee cord like across the room here, and I walk toward it, okay? When I hit it, I'm going to start doing what? Right. Or I'm actually going to be accelerating backwards. Okay? I keep walking into it. Eventually, I'm going to come to a stop and then get shot back the other way. Okay? So this would be the part where I would be stretching the bungee cord and it would be slowing me down. This would be the point where I actually change. I would stop instantaneously. And it says here, like, the bird does stop instantaneously. What's its velocity right here? 0. Right? And then it starts going the other way. Right? So this part would be, whoops, put the eraser down. Okay? This part would be where I get shot backwards the other way by the bungee cord. Does everyone kind of follow that? Okay? So I almost always put a question that looks like this on there, and I ask exactly that question. Okay? See if you can interpret that graph and say, all right, yes, the acceleration is positive through this entire section, like section E, but the direction of flight only changes at 8.5 seconds. Okay? Questions on that one? Okay, so this is a position versus time graph here in question number 1. Okay, and it's asking us, describe the motion of the object from the graph above. What's the object doing in this part of the graph? Remember, this is a position versus time graph. It's moving at a constant speed or at a constant velocity in a positive, or in this case, north direction. Okay, what's it doing right here in the flat part? It's stopped, right? Okay, its position is not changing. Okay, and then here and here and here, right, moving at a constant velocity in a southern direction, right? And then this would probably be the fastest part right here because it's the steepest part of the graph. All right. Okay, and then this would be our velocity versus time graph. Okay, so if I have this velocity versus time graph, what's the object doing here in the flat part?
Constant speed at 5 meters per second.
A constant velocity of 5 meters per second forward. Okay, remember, anytime you say constant velocity, you need to put a direction on that because velocity is vector. Okay, so you need to have a vector on there. Okay, so forward is our vector. All right, and then this part of the graph here is instantaneous. Okay, so the object is actually instantaneously stopping and then turning around and going backwards. Okay, how do I know that this part represents it going backwards? Because it's negative. Okay, sometimes if I give people a description of this graph and ask them to draw this graph, this is what they draw for me. Okay, so I'll tell them first the object travels forwards at 5 meters per second for 10 seconds. So they draw that, right? And they get here to 10 seconds and like, okay, perfect. Then it turns around and retraces its steps at negative 5 meters per second for 10 seconds. This is what they draw for me. What did that object do?
Time travel.
That's right. It went back in time. right? Time only goes this way. It's saying that at time 10 seconds, you went backwards in time to time 0. You can't do that unless you know something I don't. If you have a time machine at home, we gotta talk. Okay? Because there's things in my life I change, I do differently. All right, so just realize, guys, that that is actually a common mistake. I mean, we kind of make fun of it, but it's actually a fairly common mistake. We don't want to make that, okay? Graphs always move forwards in time because that's the only way we can move, is forwards in time. Okay? We can go different directions, but time only goes forward. Okay. Okay. Question number 1. You guys don't know what ticker tape is, so I'll phrase this differently. Let's say I've got a car. I've got 2 cars. They both have a oil leak, so they're dripping oil at a very constant rate. Okay? They both drive away, and I don't watch them leave. From the oil drops, can I tell which one accelerates and which one moves at a constant speed? Okay? How does the constant speed one look?
The drips are constantly spaced.
Right. The drops would be the same distance apart. If it's accelerating, the drops would get farther apart. Okay? In the same way that an acceleration, or the graphs of those 2 objects would look like this, right? Here's the constant velocity cart, okay, or car, and then this would be the acceleration car. Okay? It goes further each second than it did the second before. Okay. All right, I want you guys to try 7 and 8. I want you to determine the displacement of the objects in those 2 graphs. And I'll give you a few minutes on 7 and 8, okay, to try to calculate the displacement of these 2 objects in 7 and 8. Okay, so on our first one here, we want to calculate the displacement. And we remember that for a velocity versus time graph, or for anything, if we want to calculate displacement, we take average velocity and multiply by time. Okay. So I take average velocity and I multiply by time. So in this first 5 seconds, okay, the velocity is constant. So that's pretty easy. I take the velocity, 5, and multiply by the time, 5, and I find that it goes 25 meters, okay, during that part of the graph. Now, for this other part of the graph, okay, I actually kind of have 2 shapes. I probably could have done this whole bottom bar at one time, okay, but this will be another 25 here, because it's the same shape. Everyone okay with that? Okay. And then I have how far does it travel while it's accelerating? That's this part of the graph. Right? So the average velocity during this part, it goes from 5 to 15. So its average would be 10. Yeah, halfway in between. Okay? Half the time it's going faster than 10 and half the time slower than 10. Remember, we calculate this by going the base, 5 seconds, times the height over 2. Right? So for this graph here, we have 5 again times 5, so we got 25 there. So our total distance travel, or sorry, our total displacement here should be 75 meters east. Okay, everybody all right with that? Okay, all I did was calculate the area under the line, which is taking average velocity and multiplying by time. Right? You have to do the same thing in number 8, except you don't have any triangles in number 8. So I'll give you a couple minutes to get number 8 done, and then we'll look at it. Okay, so let's have a look at the last one here then. So we've got this velocity versus time graph, and in the first 5 seconds, okay, so to this point here, it travels at a constant velocity of 4 kilometers per second up. I don't know what this thing is, but it's really fast. Okay, so 4 kilometers per second up, okay, multiplied by 5 seconds is going to give me 20 kilometers. Okay, everybody okay with that? All I did was this calculation again. The average velocity was 4 kilometers per second, multiplied by 5 seconds gives me 20. Everyone okay there? Okay. And then here, okay, it moves at 2 kilometers per second for 2 seconds. So that's going to be, okay, another 4 kilometers, right? And then here, 4 kilometers per second for the next 3 seconds. So that'll be 12 kilometers. So the total displacement of this object is going to be 36 kilometers up. All right, that ringing a bell? I would suspect you might get a question like one of those tomorrow on your quiz, which will be posted by 3:30 today. You should definitely check it out tonight, okay, so that you are ready for it for tomorrow. Okay. We'll skip those ones for now. Okay, in your workbook package, okay, so if you go into Google Classroom here, okay, we're going to work on just some stuff from a worksheet here to kind of practice and review this in preparation for the lab that we'll be doing very soon. Okay, so in the classwork tab of Google Classroom, okay, you've got your notes package, you got your kinematics workbook. That's what you need right now. Okay, just click on that, and you're going to go to okay, so you're going to go to page 4, and let's say we'll look at, that's not what I want. I forget where I put it. Okay, 25 meters per second. Oh, sorry, that's not the right one, is it? Still not the right one. All right, I'm just going to be smart about this and do this. Okay, so we got this car moves along a straight road at a constant velocity of 75 kilometers per hour for 4 hours, stops for 2 hours, then drives in the reverse direction at the original speed for 3 hours. Plot a velocity versus time graph for the car. All right, so first off, my velocity versus time graph has to have a positive and a negative side to it, because for part of it it's going forwards and for part of it it's going backwards. Okay, and forwards and backwards, okay, are simply defined here as positive and negative on our graph. It never actually says north or south, so I'm not sure why it says north here. Okay, but we've got positive 75. Okay, the other velocity I'm going to travel at is negative 75, and then I'm going to be stopped for a little while, so I really only need those 3 numbers on my axis. Okay, and then I'll need 4 hours, 6 hours, and 9 hours. Because that's what's going to go on here, right? We're going to travel at 75 meters or kilometers per hour for 4 hours. And then we're going to stop for 2 hours. Then we're going to go backwards for 3 hours at 75 kilometers per hour. There's my graph. Okay, that's what my velocity versus time graph should look like. It shows me going forwards at 75 for 4 hours, backwards at 75 for 3 hours, and stopped for 2 hours. Okay, when I'm stopped, my velocity is 0. Everybody okay with that? All right, the next thing it asks for is find the area under the graph for the first 4 hours. Okay, this shouldn't be meters, it should be kilometers. But okay, so we're going to have 75, okay, times 4. Okay, it's going to give me 300. So this here will be 300 kilometers. Okay, all I did was take average velocity and multiply by time. How far did I go here? 0. There's no area under the line. The line's on the x-axis, so there's nothing to calculate there. Okay, and then I'll have this part here where we traveled at 75 kilometers per hour backwards, okay, for 3 hours, which means we're going to be looking at 225 kilometers. Okay, so if I go 300 kilometers forward and 225 backwards, that means I ended up 75 kilometers ahead of where I started. Everybody all right with that? Okay, nothing too difficult about the calculations there as long as we get the graph the right shape. Okay. Now, number 10 is a little more involved. Okay, so I want you to take your time on number 10. Okay, again, you're drawing a velocity versus time graph for that one. convert your minutes into seconds when you're doing this, because it'll make your life a lot easier, okay, when you're making the graph. All right, so I'll give you a few more minutes on number 10, and then we'll walk through that one. All right, so let's have a look at number 10 here, guys. So we're supposed to draw the velocity versus time graph of this motion. So we can start off, it's pretty easy for at least the first two parts. Okay, travels at 25 meters per second for 10 minutes, which is also 600 seconds. Okay, so I'm just going to go like this and say that this here is at 600 seconds. Sorry, I should go all the way to the x-axis. All right, then because they run out of gas, and we're just going to say that they instantaneously ran out of gas. Okay, and stopped and got out of the car and got the, we're faking it a little bit here. Okay, they're going to walk for another 10 minutes at 1.5 meters per second. All right, so that takes us to 1,200 seconds. Okay, then it says after they fill the can, they walk back to the car, but they walk back at a slower rate. So if it's slower, will it take them longer? Okay, but I don't know how long. It doesn't tell me. Can I figure it out?
Yeah.
Yes, because I know how far it is, or at least I can figure out how far it is from the car to the gas station using this section of the graph. Okay, so if they travel at 1.5 meters per second for 600 seconds, then I can calculate their displacement by going v times t. So that'll be 1.5 times 600 seconds, which is 900 meters. Right, so I know it's 900 meters from the car to the gas station. Everybody okay with what I did there? Right, all I did was calculate the area under the line. Now that I know it's 900 meters from the car to the gas station, it's also 900 meters from the gas station back to the car. I can figure out how long it will take to get back to the car, walking now slower because you're carrying a heavy can of gas. All right, so if I go 900 over 1.2, that'll tell me how long in seconds it takes to get back to the car. All right, it's going to take 750 seconds. So that's going to mean my next mark on the graph is going to be at 1,950 seconds, and it's going to look like this. Okay, we walked at a slower rate back to the car. And then drove all the way back home at 25 meters per second backwards. So that looks exactly like the first part of the graph, except it's below. Okay, and that would take them 600 seconds, so this would be at 2,550 seconds. Right, that's what our graph should look like. Everybody follow what we did there? All right, let's have you guys try you know what, we did those two yesterday, didn't we? They look really familiar. I'm sure we did those yesterday. Okay, I want you guys to try this one. Okay, you don't have it in your notes package, but okay, give this one a try here. So we got a velocity versus time graph. I want you to find the distance the object travels in between 0 and 5 seconds, okay, between 5 and 10, between 10 and 15, and over the entire trip, okay, using that graph. Okay, give you a few minutes on that one. So, just got a basic velocity versus time graph, and this is exactly the kind of thing I would put on a quiz for you to do as a velocity time graph. Calculate the displacement or calculate the acceleration in some cases. Okay, so if I want to calculate the displacement, or in this case they ask for the distance traveled, okay, between certain time intervals, then okay, take average velocity times time. In other words, I'm finding the area underneath the line, so I'm just going to break it all up into different shapes, since they basically asked me for all of the shapes at some point. Okay, so the first part A, says between 0 and 5 seconds. So I've got a triangle between 0 and 5 seconds because the object is accelerating. Okay, so I'm going to take the base, 5 seconds, and multiply by the height over 2. So 5 times 15, and it should give me 75, right? Okay, so 75 meters here, right? And then I've got 5 times 30. So I've got this big rectangle here. That's going to be 150 meters. Then I'm going to have this rectangle here, which will be 5 seconds times 20. okay, which should be 100. And then I'll have this small triangle here that has a base of 5 seconds and a height of 10. So 5 times 10 is 50 divided by 2, so this is 25. Okay. And then I've got this rectangle here, which is the same size as this rectangle, so I can save myself some time. Okay. Just write 100 meters there. And then I've got this triangle that is 5 seconds by 20, okay, divided by 2 is 50 meters. All right, so now I've got all of my distances. So the answer for part A, 75 meters. Okay, the answer for part B between 5 and 10 seconds was 150. Between 10 and 15 seconds was 125. And then if I want to find the total all the way to 25 seconds, I add them all together, and that should come out to 500 meters. Okay. Everybody all right with that? It's ringing a bell. We can handle this? Good, because you're going to have to. Okay, on the first 2 labs we do, the first lab is on position versus time graphs, and then like a week later we do one that's going to have velocity versus time graphs. Okay, so we got to be ready to use both. When I'm talking, you're not. So, thanks. Okay. No, that one we'll skip. And that's all I've got. Okay. So, some things that are going to come up here, guys, over the next little while. Okay, we're going to have a lab, and I'm looking at like Monday most likely for that. Okay, so we'll be doing a lab on Monday. That'll be a constant velocity lab. So we'll have the new carts that we got, okay, and we'll be just graphing their motion as they move with a constant velocity. It's very easy. Okay, similar to the graphing lab you would have done in Science 10 with the little motorized trucks. Okay, down the atrium with the measuring tapes, except like the data will be way better because you won't have somebody putting down a sticky note on the tape as you go. The measurement is far more accurate than that, and it takes way less time. So we'll be doing a lab kind of like that, but the questions will be more in depth. And then we'll be probably, maybe even today, starting to talk about adding vectors. Okay, moving into vector addition for sure tomorrow, probably Friday. Okay, and then we'll be back to graphing next week to do the lab, and then we'll be talking about acceleration after we get done all the vector addition stuff. But once we start into vector addition, we do that for a while, because it takes us a while to get through everything. That's why I like to have the lab kind of in the middle. Otherwise, you're just doing vector addition for like a week and a half. Okay, straight with no break. So we'll kind of break it up a little bit there. But we'll probably start looking at that here in the next 5 minutes or so, but I'm going to give you a 5-minute break here, okay? So you can check your phone, whatever, go get a drink, go use the bathroom, but be back here by 1:35, please. Okay, and if you're going outside to the hallway, don't be noisy.